So, helium unit was not built in Qatar, Gas and Ras Laffan before 2004. Until 2004, it was not built in our LNG train. And the reason is that the natural gas in general contain a very small amount of LNG. But in general, greater than 0.3% helium is considered economically viable to extract helium from natural gas. So if we have greater than 0.3% helium in our natural gas, this is considered a good, good driving force for extraction of helium. So if we have helium more than this amount in the natural gas, sorry, in the natural gas, so this means we can is good to extract this helium, and helium itself is a product that has a lot of applications. It's a kind of inert gas that has a lot of application in industries, and also the natural gas that we will sell has higher quality. So in general, okay, low concentration, if it's lower than this, is not economically, affordable to extract them. And but since we are liquefying a huge amount of natural gas in the LNG train, so it is good to extract this helium, because since we have a huge amount of natural gas, for sure, although the concentration of helium in natural gas is low, but we can have a huge amount of helium since we are treating huge amount of natural gas. So in the LNG train, we can concentrate helium by almost 10 times. Before the installing helium unit, before 2004, when there was no helium unit, majority of helium was extracted in the nitrogen rejection unit, in the nitrogen flash drum. Okay, it's when we decrease the pressure by Joule-Thomson effect, and then we were removing nitrogen. The majority of helium could be rejected, could be extracted in that unit. Now here, like in helium extraction unit, instead of one step of flashing, we will have two steps of flashing that you will see it later. Okay, so I'm gonna talk a little bit about these two figures that you have in your slide 4 and 5. We have, like, you have seen this photo. This photo is kind of those those first photos that you saw in Unit 1, Unit 2, or maybe other units. So it shows the overall LNG train. Okay, what's happening in the overall LNG train. So we had raw natural gas that was going to mercury removal, then acid gas removal, dehydration unit, then we were sending it to the chilling and liquefaction, and at the end of liquefaction, okay, we will have a helium extraction. The helium extraction unit is located here. Okay, then we will send it to the filter and nitrogen rejection. But helium extraction is kind of considered between these two units, nitrogen and liquefaction. And after we extract helium, we have to purify it. Okay, we have to purify, because here we will remove crude helium. Then after we will purify it. After purifying, we have to liquefy it. We have to convert it to the liquid phase, and then we will send it to the storage, export, and sell. This is the overall view of this process. This photo also shows, with some more details that what's happening in liquid extraction unit. So we have our natural gas that goes to several treatments, procedures, or step or units. Then it will be liquefied. In the liquefaction unit, we will liquefy the major part of the LNG that we need to sell. So we have methane and for sure some heavier hydrocarbons. And then we have methane, another stream that contains methane and a large amount of nitrogen and helium that we will send it to the helium extraction and purification unit. In helium extraction and purification unit, we remove helium, we will send it to the liquefaction and then storage. And another stream that is going out of this unit is nitrogen, methane and nitrogen that will be sent to the nitrogen rejection unit. Okay. Okay. Now I'm going to continue with this slide. So the theory, helium extraction theory uh, is often decreasing the pressure. When we have a high pressure stream, when we decrease the pressure, especially if you have a two-phase or liquid phase stream at high pressure, then we will decrease the pressure and send that stream to the flash drum or flash unit. What will happen? We decrease the temperature, the pressure, and a, a big amount of that liquid will be vaporized. When it is vaporized, what will happen? The component, the elements, the molecules that are lighter, they will go to the vapor phase. Okay, so this is the theory of, I mean, like using the change of pressure that changes the solubility, because the solubility at higher pressure is more. Helium in the gas phase, uh, when you put it at high pressure, it will move to the liquid phase. It will move, stay in the liquid phase. The solubility will increase. But if you decrease the pressure, the solubility of helium will also decrease. Okay, so the theory is decreasing the pressure in the flash drum, that in that case, the solubility of low boiling components like nitrogen, helium, hydrogen, and argon, which are light molecules, the solubility of these molecules in the liquid phase will decrease, and they will be released from the LNG gas. Helium has a lower solubility than nitrogen in the LNG. Why? Because helium is light. It's a very light molecule. So, but nitrogen is heavier than helium. So, if helium or nitrogen they're supposed to be in the liquid phase, we expect to have more nitrogen because helium is light. It will prefer to stay in the gas phase. So that means if we have a flash drum, okay, at higher pressure, nitrogen will stay in the liquid phase, while helium, which is lighter, which has a lower solubility, it can go to the gas phase, to the vapor phase, even at higher pressure in the pressure in the flash drum. Okay. Okay. The majority of refrigeration required to operate helium recovery process. So, the helium recovery process is mainly, the theory is mainly based on the Joule-Thomson effect, through a valve, the Joule-Thomson valve, that we will reduce the pressure, and in that case, we change the solubility, and helium will be separated. And moreover, we need additional refrigeration in helium extraction unit, and this is needed to, because the unit is not usually perfectly isolated, so there will be always some heat that will be absorbed from the environment. So this change in the heat that is absorbed will change the temperature and operating pressure as well. So we need to have always some refrigeration, additional refrigeration, to make sure that we will overcome the heat that is absorbed from environment. Okay, So now we are going to talk a little bit in more details about the on the helium unit. So you have here in this slide, you have the major components involved in the helium unit. So I'm gonna start. I'm gonna read from this slide here in the left side, in the right side, and then I will mark those equipment in this part. So as shown in the process flow diagram, okay, the photo in the left side, the unit comprised of the following equipment. We have a cold box. So this green line here, you see all the way here, and then here, and here. All the way here, this green line, okay, that I show you with these four arrows. This green line is the square green, like box is a cold box. All the equipment, the majority of the equipment is located in this cold box, which is isolated from the environment by using some special isolation material. Then we have the LNG Flash Drum. This is the LNG Flash Drum. All of them are inside the cold box. We have Crude Helium Separator. This is which is again the crude oil crude helium separator is also kind of flash drum. Okay, so is this one main heat exchanger. This is your main heat exchanger here, and crude helium warming heat exchanger. This is your crude helium warming heat exchanger that after that the crude helium will be sent to the purification and liquefaction unit. So those are the four main components that we have in this unit. Okay, so now I'm gonna explain them a little bit in more detail. So let me clean it first. Okay, so we have a cold box. Okay, the cold box is a cold box. The normal carbon steel plates, okay, normal carbon steel plates that enclosing, it has two flash drum, it contains two flash drum, okay, a heat exchanger, some valves, some pipe works, piping, and some instruments. Okay, all of them are located inside a box. So the advantage of cold box. The cold box eliminates a lot of work at the job site, such as isolation, piping, and installation. It's already a package that is ready to use, and it has already a good isolation and many other features. So this using such a cold box help us to save a big amount of time and expense in construction of units. Cold box contain pertile. I already talked about pertile isolation. It's a natural isolation material that surround the cold box, and it has also a nitrogen purge system. Before starting up the process, the cold box, the unit, we have to use nitrogen. We have to purge nitrogen to make sure there is no moisture, no impurities, and so on. So nitrogen positive pressure is regulated at about 0.34 bar gauge, which is 1.34 absolute pressure, a little bit higher than atmospheric pressure, through a needle valve on the roof. And why we need nitrogen purging? We need nitrogen purging to remove any moisture during the pre-startup or the startup. We can use also check, the leakage through the cold box by injecting nitrogen. Okay, and why we have to do that? Because if there is any leakage through the cold box, so the pressure can drop. So we can we can inject nitrogen. We can set the pressure of the unit, set the pressure, and after a while we can see if there is any drop in the pressure or not. In that case, we can detect the leakage problem. Okay, again, some additional information about the nitrogen purge system in the cold box. So we use the nitrogen purge to prevent any air from entering the system, to prevent any moisture, to maintain dry and inert atmosphere, no reactive gas like oxygen in the system. And when like we cool down the system, we might create some vacuum. This vacuum might even damage the instruments, the unit. So using such a nitrogen purge help us, to avoid the creation of vacuum during the cool down. Why? Because like when you cool down a gas, okay, the volume of the gas decrease. So this decrease in the volume can create a vacuum. And as I said, to remove moisture and avoid, why we have to remove the moisture, because any moisture that is available in the system can cause, the ice formation that can damage the, the equipment. Pertile, that is used as a isolation material in the cold box, is a what's the advantage? It has excellent thermal properties for isolation. Is a natural material, so it's low in cost. It's easy handle. It's very easy to handle it and install it. It doesn't shrink. It doesn't change its volume. It's very light. The density is 10 times, almost 10 times, less than water. Less is about 120 to 150 kilogram per cubic meter, and it's most important is non-combustible. It doesn't catch fire. Okay, so those are all the great, excellent properties of Pertile that we have. And as far as I know, India is also producing a lot of Pertile. Okay, so it's one of the, main producer, but I'm not sure. I have to confirm this. This is just what I saw in some, like articles. Then, okay, let's now talk a little bit about the process description to see what's going on in the process. So we have the cold LNG stream. It means here the cold LNG stream that is that contain a large amount of helium. Okay, that is coming from where? It's coming from main cryogenic heat exchanger. It will enter the intermediate flash drum. This is your intermediate flash drum. All right. A flash pressure of 4.5 bar absolute. So you see the pressure is almost 4.5. It leads to helium recovery of about 87.5%. So 87.5% of helium will be recovered here at the top. Decreasing intermediate flash pressure drum to increase helium recovery, but a decrease in the helium concentration. Okay, so we can still decrease the pressure of this flash drum, okay, to even lower than 5 bar, 4.5 bars. But what will happen once we decrease the pressure here? We can get more helium here, but in the same time, we can have more other molecules, more other heavier molecules at the top. So although the amount of helium will increase in the upper product, but the concentration will also decrease. Okay, so there should be a compromise to see which one is more. We have to kind of optimize the process and see which one is more uh, suitable for us for the application that we have. The liquid phase. from the bottom of the drum is then subcooled in nitrogen column reboiler and subsequently flashed in the nitrogen rejection flash drum. So this liquid phase here from the bottom of this flash drum, it will be this flash drum, it will be sent to the nitrogen flash drum where we reject the nitrogen from that stream. Okay, so it will be sent to the nitrogen rejection. Gas phase from the top of intermediate flash drum, it means this gas phase here, this vapor phase, is further cooled in the helium recovery heat exchanger to condense all the hydrocarbons. Here, so you will send this gas phase to this heat exchanger, the helium recovery heat exchanger. So it will be cooled down. And in that case, you will cool this and you will create a liquid phase or some kind of two phase, both liquid and vapor. That most of the hydrocarbons here in this stream will be liquid, heavy hydrocarbons will be liquefied, and then you will send that stream to a second flash drum, a flash drum that has a much lower temperature and operating pressure. So from top, it will be sent to the intermediate flash drum. I'm talking about this one here. And it's cooled down in the helium recovery heat exchanger to condense all the hydrocarbons. Then, these hydrocarbons are separated from the crude helium vapor in the helium separator flash drum. So after the heat exchanger, they will be sent to the separator or to the flash drum. I call it also flash drum, that we can separate liquid from the vapor. Both liquid and vapor stream are used as cooling media in the helium recovery heat exchangers. Here, since we decrease the pressure, so we will decrease the temperature as well. It's like a Joule-Thomson effect. Then we have both vapor and liquid that are colder than this stream that is coming from, let's say, 1 minus 1 minus 50 why is 1 minus 50? Because coming from main cryogenic heat exchanger. So we can use both this liquid and vapor, which is coming from this flash drum at lower temperature. We can use it in the recovery heat exchanger for cooling purpose. Since they have lower temperature, they can be used in this heat exchanger for cooling purpose. Then the recover, let me just make this a bit cleaner, not to confuse you. So after they are sent to the cryogenic heat exchanger, we have the liquid products. This liquid product that will be sent to the fuel gas system. Okay, will be sent to the fuel gas system, and the helium, which is a crude helium, and also is kind of pure stream of helium. It will be sent first to the kind of warming heat exchanger and then to the central helium recovery unit where it will be more purified and liquefied and stored. It will be further purified, liquefied, and stored. This is the overall view of this process. Then, helium recovery unit. Let me just change this slide to this one. Okay. So once helium is like these two figures, like in the previous slide and this slide, are not really connected to each other, but I couldn't find a better photo of this, recovery unit. But still, it will help us to to learn, something about this process. So as I said, once we produce that, we are talking about this one, this part. I already talked about the upper part, okay, in the previous slide. I'm now talking about this part, okay, the helium. After the crude helium will be sent to this unit, okay, this unit to be purified. So we are now, in this unit, I mean, both the cold box and the purifying, we are kind of combining a cryogenic membrane and PSA. In some of the notes in the slide, you have, like check the notes of the slide, you have some definition about, some word that you see. PSA is called pressure swing adsorption process. Okay, pressure swing adsorption is the adsorption process that I put, a few video links for you here, YouTube videos. So if you watch them, it might be helpful, to learn more about this process. So hybrid process. Okay, so it combined this process of helium rejection is a combination of cryogenic membrane and PSA that it can help us to produce helium, which is with a purity of 99.99%. A very pure helium product that can be produced by using this process. Okay, so let's go back to our helium recovery unit that we will purify the helium. So crude helium extracted by the helium extraction unit, the previous slide, not this one, not this figure, the another figure. So is after the extraction, which is a crude helium, it will be sent to the helium recovery unit, or HeRU, for purification, liquefaction, and storage. Initial process is designed to remove a range of impurities such as nitrogen, hydrogen, water, and carbon monoxide. So the helium that is produced, that is coming from helium extraction unit, it contains nitrogen, hydrogen, water, and carbon monoxide. So we will use several steps to remove these impurities from our helium stream. How we do this? We use a two-stage membrane unit. Okay, so like here you see three stage of membrane. As I said, I couldn't find a figure that could, like match to what we have, because like we are talking mainly about the LNG train in Qatar. So, but still, like this figure is very similar to what we have here. So we use a two-stage membrane unit, like membrane like these two units, to that at the end, okay, we can produce up to 95% pure helium, uh, the 95% pure helium stream. We can further use the upgrader unit. Okay, we can upgrade this stream and we can extract more impurities in the upgrading unit. That here, this upgraded unit, we call it PSA, or pressure swing adsorption unit. That in this unit we can produce helium with a purity of 90.99%, which is a very valuable product to sell. PSA, pressure swing adsorption, it doesn't remove neon. Neon is also shown by in the periodic table, is shown by Ne. Is also an elemental, like a chemical element that is kind of considered, like is also available in the helium stream, but is not considered as contaminant. So we don't have to remove it completely, and actually it cannot be removed in this PSA unit, and that's why the purity is not 100%, is 99.99%. That a large amount of this stream with this purity is neon, that we couldn't remove them by using membrane. So this is one way. Another option that we have to purify helium is to use activated charcoal absorbers. Okay, we can use charcoal absorbers at very low temperature, at the liquid nitrogen temperature, which is very, very low temperature, and high pressure. Instead of PSA, you can see in these YouTube videos some information about PSA, how it works. I'm not going to spend time here because it's kind of out of the scope of this part of the course. But by using, okay, instead of PSA, we can use activated charcoal absorber and at liquid nitrogen temperature and very high pressure. Okay, so this is another like using the absorber. So there are some advantages when we use this very low temperature actually it's called adsorption because we are separating gas by using solid is adsorption. Absorption is usually gas to liquid. Okay, so let's call it adsorption. It can yield to a very, very pure helium. 99.999, like is a very pure helium. And the difference between the price of this helium here and this one here, okay, the difference between price of these two helium is remarkable. Okay, but PSA process cannot recover better than 99.99%. But the good thing, okay, so the advantage of this is this low temperature adsorption is that we can have a very pure helium stream, but the disadvantage is that is costly. Okay, but PSA is less costly and it can produce, a good quality helium for us. Okay, but if in one condition, if we need a gaseous helium product, PSA is less costly considering with the low temperature absorption. But if we want liquefied helium product, if liquefied helium product is desired, so PSA can be costly. Okay, after helium is recovered in the PSA unit, here, we have a pure helium. What we will do, we will have to store them. So the pure gas, the pure helium will be liquefied by using brazed aluminum plate fin heat exchanger. So we use after, if you have a gaseous, like in PSA, for example, if you have a gaseous helium ester that we need to liquefy it and store it, we will use brazed aluminum plate fin heat exchanger and also a number of turbo expanders. Turbo expanders are also, kind of devices that used for liquefaction. The rotary, like devices that they rotate at a very high speed, like about 2,500 revolution per second. It's a very high speed and very, isolated. Okay, that they will be liquefied and they will be stored in the inside very good isolated, super insulated, and vacuum jacketed liquefiers. And after liquefying in this part, we will store them, okay, in either dewars or a storage drum. Okay, I show you. I already put this figure. This is kind of a figure of a small dewar, but we have big dewars or storage drums like that. It will be stored at a very low temperature, minus 270 degrees C, very low temperature. And this is this. Like the drums, the storage drum, they are equipped with a vacuum jacket and thermal liquid nitrogen shields. Okay, so that they can, like they have a vacuum jacket that the vacuum jacket is like a flask that help to for isolation, and they have also a shield that is filled with the liquid nitrogen. Liquid nitrogen is has a very low temperature, so we use such a devices, such a vessels to store the liquid helium and transport them at very low, ultra cold liquid temperature. It's like they're called this kind of liquids, helium liquid. Liquid helium is called like ultra cold liquid. Okay, we will store it at low temperature and we will export it in that way to our final customers. Okay, some additional information about the storage. Okay, I already talked about that a little bit about the previous slide. So the storage tank for the liquid helium, they are double valve, okay, pressure container, okay, they are double valve with multi-layer vacuum isolation. As I said, the vacuum isolation prevent any heat absorption, and also like not only isolation but also radiation shield, because radiation is also one of the main methods that heat can be transferred, especially in sunny climate, like or especially the ships that are, all the time, I mean, in the sea, so they are exposed to the sun. So radiation can be, a big problem for absorption heat. So we will use a very good vacuum isolation, double wall container with vacuum isolation, and also a shield that is cooled down by using liquid nitrogen. The tanks, the container, okay, they have a capacity of about 30,000 gallons, or very big containers, huge containers, or about 1,500 liter. The boil off rate, because like when they are transported, when they are exposed to some heat, so they can create some boiled up gas, but the boiled up gas, the rate of boiled off is very, very low. It's about 0.3% per day, which is almost nothing. After that, I mean, like those containers, they are fixed with the ISO container. ISO container, like you have this photo here, something similar to that, that is used for shipment. You can lift them, put them in the ship, you can load them, you can unload them, and so on. So for Europe, we will use, like here they are stored, okay, like here they are stored in this kind of tanks, very large amount of tanks. But if you want to ship, we usually use such a container, like that. We call it ISO container. The capacity of this container is almost 11,000 liter, or 15,000. I mean, is from 11,000 to 15,000 gallons, and they are the containers that is used to ship the helium to Europe. So once they are sent to the destination, to the customer, they have to be returned for refilling. So after they are unloaded, we call them warm container. Okay, they are not cold anymore; they are warm, and they might be contaminated with some other gases once they are returned. So once they are returned to the country, we have to clean them. They have to be re-cleaned before we use them. We have to clean them from any impurities. If there is any helium remaining gas in those containers, they have to be recovered and they can be sent to the plant intake for the reprocessing. Okay, reprocessing means purifying it, liquefying, and then storage. Okay, we have a few more slides about the process, shutdown, process, startup, and so on. So I'm going to talk a little bit about that part. Let me just go to this slide. So, okay. Okay. So, yeah, just need to clean this slide a bit. Okay. So, for the startup, we have few steps, okay, that I'm gonna explain one by one here. We have, okay, the helium extraction unit. maybe a startup or restart up during the startup of main cryogenic exchanger. So this unit, the helium extraction unit, this unit I mean here, so it can be started up or it can be restarted up by the same time that main cryogenic heat exchanger uh, is being started up, or it can be started up even independently, and we can cool it down because the low temperature here is very important, very crucial. So we can start it independently by using some defrost gas and cold feed gas that is coming from the overhead of reflux drum. You remember we talked about the scrub drum, reflux drum in other units. So at the end of this slide, you have some figures, I think, at the end of this presentation. Yeah, I just put some figures for you here. What was the flash drum that we had, reflux drum that we had, a scrub drum. We already talked about all of them in other units. Then the videos are also available on, are provided to you. So, okay. So we can use the frost or cold feed gas that is coming from the overhead of reflux drum, which is connected to the scrub column. Okay, and we can start the unit by using those gases, and then we can introduce the LNG. We can introduce the LNG that is coming from main cryogenic heat exchanger. So those are the procedures that we have to follow. I'm just going to read on from them, and if you have any question, you can ask me later. So the general, okay, what we have to do kind of general status checkup. We have to check all the instruments, the utilities, the feeds that we need. We need to do kind of continuous nitrogen purge to the cold box in operation. Why we use that? To remove moisture, to avoid vacuum and so on. We already had one slide that we talked about the purpose of nitrogen purge. We have to confirm that all related units before and after they are commissioned and they are in operation. We have to do kind of a complete check for the valve positions in the unit and make sure that all the blinds are correctly positioned. Blinds are also used to open or close, a pipeline when we cannot really rely on the valves, when we don't want to put a lot of pressure on the valve, so we can use those kind of blinds. So usually to block a pipe, let's say temporarily, uh, without like affecting the valve, putting a lot of without putting a lot of pressure on the valves. Tightness test by using okay, so we will use gas, like let's say nitrogen gas, inert gas under pressure to do kind of leakage and tightness test. We will send initial warm defrost to remove any moisture and completely defrost the unit until the system moisture content is met. So we will use warm defrost gas or warm nitrogen to remove the moisture, and then at the end we have to kind of do some measurement to make sure that the moisture content of the unit is below the specification. And this is to avoid any ice formation that can damage the equipment that we have. Then, okay, for the startup, again, then we have to warm up or do some initial defrosting for the main cryogenic heat exchanger. We have to start up the propane refrigeration unit. We have to start up then a scrub column and cool down the system by flashing some feed gas from the overhead of reflux drum or scrub drum. We will then carry out a pre-cool down procedure for the main cryogenic heat exchanger. We cannot decrease the temperature suddenly from atmospheric temperature to minus 170. So it will be done in several steps, in few steps. This is, first of all, like technically we don't have that power to do this cool down process in a very short time. Second, the change of the temperature can, change. It will change the properties, the physical properties of the metal parts of the vessel. So if you do a sudden change in the temperature, you can damage the vessels, you can damage the equipment. So that's another reason that we use such a process, several steps to cool down. Then after the first step of cool down, we will have second pre-cool down procedure that uh, we will decrease the temperature to minus 50. After that, we will start the multi-refrigerant compressors, multi-refrigerant compressors that we already talked about them in other units. And finally, we will have the final cool down that we will decrease the temperature from minus 50 to about minus 150. Okay. Then we will do the final cool down and startup procedure for the helium unit, helium extraction unit, nitrogen rejection unit, and we will follow the startup procedure for the fractionation unit. Then after that, we can stop the nitrogen purge not stop, we can decrease the nitrogen purge in the helium extraction unit, and we can introduce the feed here, it means here, to the unit and ramp up the load and we introduce the feed and increase the flow rate to the design flow rate. And after that, we have to check the LNG products that we have. Okay, the LNG products and the helium that we are extracting, the crude helium that we are producing, to make sure that it follows the specification needed. And after a while, when we make sure that operation is under control, we will bring it to the normal operation and we will control it at a very steady state operating condition. For shutdown is also simple. First of all, we shut down the helium unit first, okay, by switching the helium to the fuel system. Okay, we will switch the helium. As I said, we have several valves in this unit that we can switch, streams, from one pipe to another, from one stream to another one. So we will switch the helium to the fuel gas system. It means here. Okay, once the helium is blocked from the product line, the cold box bypass valve is open. And okay, once we will make sure that helium is sent to the fuel gas system, here we have a bypass valve. Before here we have a bypass valve that instead of sending the natural gas to the cold box, we can have a bypass and send it to another unit. Okay, here we will have a bypass valve. So that bypass valve is open, and we will close the cold box feed valve. Cold box feed valve is here. We will close it and we will open this bypass valve here. When the feed valve is closed, it means that the valve that we will have here is closed. The excess liquid is drained from the intermediate flash drum before the return shutdown valve from the cold box, and the helium to the fuel valves are closed. So, like once we close that, we will drain any liquid that is remaining in this intermediate flash drum. We will retain it. Collect it. before we close any other valves. Let's say we have some shutdown valve here, emergency shutdown valve. So before those valves are closed, we will drain any liquid remaining in this part. There might be some operational problems, okay, that we need to consider. So this is kind of our, I think we have 2 more slides to finish this unit. So there are some operational problems that we might take into account, and we have to avoid them. Is mainly about the utility failures. So there might be some loss of instrument air. You know that most of the pressure valve, most of the valves, the flow meters, the valves that open or close, or even emergency valve, they are pneumatical valves. They work based on a pressure line, that pressurized air that is connected to them. If we change, like if we change the pressure of the air inserted on the valve, so we can close or open the valve. Okay, so like we have to make sure that we have always a pressurized air supplied to the instruments. If this instrument is lost, we have to put move the valves to the safe position. Either they have to be closed or wide open. This is depending to the protocols that we have. And we have to also, close the emergency valves, shutdown valves have to be closed. I mean, like the feed valves to the unit, to the exchanger, they will be all closed. So none of the equipment, they will be under pressure or under high temperature. There might be a loss of electrical power for any reason. Let's say stormy weather. So in that case, we need a total plant shutdown is required if there is no electrical. But usually we have a utility unit that can supply, that has a generator, electrical generator that produce electricity. If there is a seawater or cooling water failure, if we have a seawater failure in the seawater, what will happen? So the crude helium warming heat exchanger, the temperature will decrease. Okay, if we don't have that cooling water, the uh, the temperature will decrease, and uh, we need to activate the interlock crude helium mode selector. That is, again, a device that is designed in the plant. That is, inserted in the plant to like avoid having products which is doesn't meet the specifications. Okay. And some operational, some safety, operation safety that we need to consider. Uh, we need to do our best to avoid formation of any combustible mixture, like if oxygen is leaked to the system. Oxygen is very combustible. Gas, or if there are hydrocarbons in the system, we have to control them. We have to avoid the formation of those kind of mixture. We have to avoid any ignition sources, okay, to avoid fire. We need to, like make sure that the operators are working in the atmosphere that is not deficient in oxygen. There is enough oxygen for them, and there is also proper ventilation system design in the site. We have to avoid frostbite. Like in LNG in general, we have a cryogenic process, a very low temperature, very cold environment. So touching those equipments, like at very low temperature, can cause frostbiting, okay, or frostbiting skin. So that will damage, the workers, the operators. So we have to make sure that we control all this situation. We have to avoid any high pressure formation or leakage. We have to check the cold box leak. That is important for the unit, for the specification that we need. And we have to check any suspected Cryogenic leak in the cold box. Okay, any hydrocarbon, any gas at low temperature that is leaked has to be carefully managed. So that was all for this unit, and I hope you enjoy it. And please review this unit, please watch it, and if you have any question, I will be always happy to answer. Thank you.